In this video, we're going to consider the asymptotic runtime analysis of several methods related to array-based lists and several methods related to linked lists. We're going to start with the indexing operation for array-based lists. And so here we have a few lines of code, mostly comments, that represent the actions that need to be taken to get the items out of a specific index in an array-based list. The first thing we do is find the beginning of the array, and then assuming that 8 chunks of memory are used on your machine for each address that is stored, we will find the correct address corresponding to our specific index, and then go fetch the value from that address. So we see here on line 7, that's the first time something's happening, and that's just getting the address of a specific item. That's one time step. And then we have 1, 2 arithmetic operations and an assignment. That's 3 total operations. And then we will get the value and return it. That's 2 operations. So overall, the time needed to get an index, the item out of an index, which we'll call t of n, is 1 plus 3 plus 2. That's 6. Since that's just a constant, we know that t of n is big O of 1. Next, let's consider the insert operation for array-based lists. We get the length of the list and assign that to n. So line 19 corresponds to 2 operations. We do another assignment on the next line. We do a comparison each time through the while loop, and we do 2 indexing operations and an assignment. So this is 1 and 3. And then we do arithmetic and assignment. That's another 2. So this whole while loop is 6 times the number of iterations. And then finally, we want to store the value x in the proper place. So that's an indexing and an assignment. That's 2 steps. And so we can see that the time for insertion is at the beginning 3 steps, at the end 2 steps, that's 5, plus 6 times the number of iterations of the loop. How many times does the loop happen? Well, once for every position greater than or equal to I, from I up to n. So that's going to be n minus I times. So times the quantity n minus I. That's a worst case scenario. You're inserting at the beginning, so this will be n minus nothing. And so n would be the absolute worst case. So if we consider the fact that t of n will be worst case 5 plus 6 times n, that's the biggest this value can be. We can ignore the 5 because that term is a lower order than 6n, and we can ignore the 6 because that's a constant multiple. So here we have that the time for this operation is big O of n. The last operation we'll look at for array-based lists right now is the append operation, which we see involves getting the length and assignment. That's 2 operations. And then indexing and assignment. That's 2 operations. So ultimately, this means the time for this operation is exactly 4 steps. meaning that our time is big O of 1 since 4 is a constant. To recap for our array-based lists, both indexing and appending can happen in constant time, whereas insertion actually depends on the length of the list. And so here the worst case is when I is near the beginning of the list, when you're inserting near the beginning of the list. That's when it's big O of n. If you're inserting at the end, that's append, so that really is big O of 1. So the earlier you're inserting into the list, the longer this function is going to take to run. If we shift gears to linked lists, we can look at a few of the same operations for the linked lists. So in our list node class, which we're going to have to call a few of these possibly in our linked list method, so I want to look at these first, we see that in the constructor, we just make 2 assignment statements. So the constructor for a list node is big O of 1. This takes constant time. It's just 2 assignments. And getting an item is just returning 1 value. Getting a link is returning 1 value. And there's only 1 assignment statement for our setters. So every single list node method is big O of 1. They're all simple assignments and returns. Nothing depends on the length of the list here because there is only 1 node that's being considered. The constructor for the linked list class is a little more complicated, and that's not one of the methods that I want us to look at right now. I want us to look at the analogous ones for the array-based list methods that we've already looked at. And so I want to switch over to those. And first we see our length is still just a return statement. So this method is big O of 1. And our insert method is starting with the list node constructor, that's big O of 1, and an assignment. So this line is constant. We have arithmetic and assignment, also constant. On this line we have a function call. So we have the arithmetic of subtracting 1, the assignment of previous, which for big O analysis does not matter. But here we have to consider what the asymptotic analysis of underscore find, that method is. So we'll have to come back to this line. Here we're calling one of our list node methods, actually 2 of them. And so this is all constant time, as we just saw. And same thing here. So really insert is going to be some constant. The time for insert is going to be some constant. I didn't count specifically. It doesn't matter if all we care about in the end is big O. It's, whatever the constructor for list node is, which we saw was 2, and then assignment, so that's 3, arithmetic 4, assignment 5. Okay, so there's 5 before the function call. There's 2 included in this same line as the function call, the arithmetic and the assignment. There's a function call here, a function call here, but these functions we just looked at and we know that they are 1 or maybe 2 operations, but they're all big O of 1, so they're just constant operations. So overall, the insert method is some constant that I don't care about, plus the time for the underscore find method. So if we scroll down to underscore find, we see there's a loop. I'm leaving this one as an exercise for you to think about. So how much time does the underscore find method take? But as soon as you can answer that question, you get the answer to insert for free. Insert will take whatever time find takes, plus a constant, but big O notation isn't going to care about the constant. So we can ignore that part, and the big O analysis of insert will be exactly the same as the big O analysis for underscore find. The other method that we looked at for array-based lists is the indexing operation. And so if we look at that in this context, again, we get a return, that's one operation. Get item, that's a call to a list node method. We saw those were all big O of 1, so these are both constant. It's this underscore find again that could possibly make it slower. So again, our time to get item in a linked list is going to be the same as the time for underscore find. So again, as soon as we know what the analysis of underscore find is, we'll know how long get item takes. You see, we'll know how long set item takes, and we'll know how long insert takes. So I'll leave underscore find for you to think about. But here we see some examples of how to analyze array-based lists. We see that all operations having to do with a single list node are constant in time. And we see that most of the methods we've already written for the linked list, aside from getting the length, which is just returning a single value, depends on the time analysis of underscore find. The next step will be to analyze this function.